So it's not just for the purpose of passing the exams. Okay, I won't be teaching you here mechanics just for the main purpose of passing the exams. Of course, there's quite a number of what you call tuition centers out there that you can go into if you want to, but I won't be teaching that here on how to pass the mechanics of solids and structures, just to pass the exams. Okay. Now, let's begin with this one here. Of course, you have your practical assignments. Yes? All of these, you can get the information from the project Moodle. So I won't be printing them out. You will be able to get all of them. I think it's somewhere here. If you go to our Moodle. Right, somewhere there. The joint Moodle. So this one part of this is also a master's class, Engineering 5053. So part of this course that we have is part of the master's class in the UK or in Glasgow itself. Should be SIT 4005. So here you go. You have two assignments. Assignment 1 will be a plate in a hole. And of course, all of the information can be taken from Moodle. This is just mentioning about the things that you need to know. The same is true with assignment 2. And then, of course, you can look at the exam performance last year. Exam solutions 2014-15. All of these are basically in your notes, in the notes. So I didn't bother printing them out because I know you're mature enough. You can simply download all of this information from Moodle. Right. Unlike when you're during your year 1, of course, I just have to print it out, talk to the library, and then print it out so you can purchase. Now I think you're more mature. So those are the discussions. So as you can see, there will be also the number of students who attempted it. In Glasgow, the class is about 150 because it includes masters and undergraduate students. So as you can see, you will be able to compare from this one here. You can open it up and then you will see how the other students fare. So for example, question 4, attempted by 14, marks range from 0 to 5, meaning nobody got it. Okay, so you have to be careful. So why are we showing this information? Of course, this will also be an information from students if they want to be strategic. Of course, end of the day, you want to pass all these courses, you want to score high to be able to get like at least second upper and so on. So, I mean, that's the truth, that's the fact. So, all of this information are also provided here. Yes, so you can have a look at this exam question. Of course, what will also help will be your peer-wise. So, previously we had peer-wise to be 2% per question. Now we have 5%. Oh, sorry, 1% per question. So, maximum of 5 only. Okay, I'm not supposed to reveal this study of mine because I still want to publish it, but the fact is that I did a peer-wise survey just to look at the performance of students from your batch and the previous batch. That was Mechanics 3. So what did I find out? What I find out was that those who are active in answering questions given if they know, they cannot benefit or there's no marks associated with that actually score higher in their total GPA year 1. So you can see the trend. Those who are in the first class, there will be much higher percentage of those who are answering rather than as you go to second upper, second lower, third class and fail. So you will see the trend. It's very clear. So I guess I think by being active, you will be able to learn more. I mean, that's the lesson there. Right. So here you go. You have 2 practical assignments. You can start if you want to. not a problem. You can download all the information in Moodle. It's no limit. So this will be due on the 6th of November. So I will be giving you your, I will be giving the marks by or after 2 weeks. Give me 2 weeks to mark that, so that you can use it to improve your report for beams and bending, beams in bending, or bending of beams, which will be due first week of December. Yes, of course, final exams and peer-wise all add up to not 105, but 100. I mean, we've done this one already in Mechanics 3. What are we going to study here in Mechanics 4? As you can see, we have Introduction to Elasticity. You've seen the curves. Where is that elasticity applicable? Now, where is that plasticity? So the next part, of course, will be plasticity. But here in the theory of elasticity, we'll focus on the stresses and strains, concept of stresses and strains. But it's not just 1D. We're looking into 3D and 2D. And of course, we will also be studying a bit of linear elastic fracture mechanics. And then, of course, we'll look at pressure vessels. Now, after that, I will be posting this one in Moodle. Now, after that, we have your Introduction to Theory of Plasticity. What's really important here are these 3 topics: your yield criterion, plastic flow, and limit analysis. And then after that, let's have further, expand our knowledge in finite element, more on the theory side, not on the use of software, on the 2D FEA. So we will be looking into shape functions, the element equation, solution procedures, and methods. So I'll just be giving a brief overview again before we move on to some of the calculations or some of the derivations of the equation. So we've done this one before. Why do we need to study elasticity and plasticity? Of course, from a design point of view, you probably want to design your structure in such a way that it won't be, or the stress acting on it won't be higher than its ultimate or yield strength. So that's from the point of view of the designer. So that's why it's important. It's important that we know the theory of elasticity. So we focus on elastic properties. That is from a design point of view. The other, of course, for theory of plasticity, it becomes important for manufacturing. So moving on to this one, we've seen this one already. So this is where you will know where the theory of elasticity applies and the theory of elasticity. So this one is the theory of elasticity, and this one will be your theory of elasticity. Actually, we don't go beyond this one anymore because it's useless. So we just go until your material strengthens because of plastic deformation. So our study on plasticity will be from here to there. Of course, we will need that knowledge in elasticity. So, of course, once it reaches that and it fails, it's not anymore our concern. We don't really need to study that because there's no engineering application. Of course, science may want to study that, but we don't really need to study that. This one is the theory of plasticity. Like I said, we won't limit our study into just 1B alone. So we have now stresses acting in the different directions, x1, x2, and x3. You can look at this one as x, y, and z. So this is just an overview. So there you go. This is where you study theory of elasticity, and from here to there, that is your theory of plasticity. From this one to failure, we don't really need to study that. Okay? So why do we study finite element? Now, why can't we just click the computer, click, 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 and then you get your model? You get your model, you apply the boundary conditions, that's it. You get your results. Happy? Well, the reason why we want to study the theory of finite elements is that it's very easy to get incorrect results from finite element software, or using finite element software. It's so easy to get incorrect solutions or answers. So at least, what can we do to be able to be guided in such a way that what we get is something useful? It's so easy to put in the geometry. It's so easy to get the boundary conditions applied to your finite element, and then just click on solve, and then you get the solution. You get all these pretty pictures. Not a problem. The question is, if you cannot validate it or verify it with another solution, it's so difficult to see whether you're correct or not. So you have to go back to the basics of mechanics and see whether your results make sense. The purpose of finite element, of course, analyze something that cannot be analyzed using analytical solution or experiments. If somebody is going to study the heart, the movement of the heart, of course, there shouldn't be any volunteer, right? Otherwise, if there will be a volunteer, then that's a big problem. Who wants to be open up? Okay, and observe the beating of the heart. I don't think anyone would like to do that. Crash test. Anybody who would like to volunteer for a crash test? I don't think anybody would like to do that as well. If you do it, for example, you do crash tests as well, you use dummy, it's so expensive, so you have to do finite element analysis. So again, this finite element method is very important, especially if your structure is complex and that you're looking at areas wherein it's so difficult or impossible to do experimental analyses. So we usually determine deflection, stresses, strains. So these are just the three things that we can determine, or what's really important, that is. Of course, if we want to view the we want to see the video, the beautiful video coming up from this analysis, to be able to understand more what's going on to our structure, then yeah, we're free to do that. So in that way, it does provide. But let's try to just look at it from the point of view that finite element is just a tool for us to achieve the goal. So we have to ensure that we do it properly. So here you go, it's easy to use the method incorrectly. So we need to know the underlying theory of the method, the strength and limitations of the element type. So that's what we want to understand in finite elements. So actually, when you get the real problem, because of the different assumptions that you have, and of course, this will also be dependent on the user, what you get is just this one. So that's modeling, and we have to accept that. So again, the first application, full application of simulation will be for this example here, Boeing 777. So from CAD to simulation, they've done a full analysis of this one. Of course, like I said, just doing this one without the knowledge in solid mechanics is not, we call this one, it's not reliable. So you have to have a good background in solid mechanics before you will be even to come up with useful results in or using finite elements. So another one, of course, the A380. So a lot of simulations have been done there. For these two aircrafts, Boeing 777 and A380, the software used was Abacus. For this kind of analysis, more complex analysis, Abacus is commonly used. For simple ones, more industry, not so much about the details, then you can simply use ANSYS. So why are you saying that ANSYS is being used in industry rather than Abacus? Because ANSYS is not a lot, half as cheap as Abacus. So that's why company prefer to use cheaper versions of, or cheaper software. Okay. So we were here last time. So going back now to mechanics, or solid mechanics, in particular to the theory of elasticity. Better now? So what we will learn first is to know how to transform the different stresses in such a way that we will be able to get the principal stresses, sigma 1, sigma 2, and sigma 3. So as you can see here, we have 3 set stresses acting on each of the face of this 3D element. There will be 2 shear and 1 normal for each of the face. So in total, there will be 6 shear components, and then we have 3 normal components. So if we're going to rotate this one, we will be able to get, so anywhere around the 3D, we will be able to get a situation wherein there will be only 3 normal stresses. That will be sigma 1, sigma 2, and sigma 3. And what are these sigma 1, sigma 2, and sigma 3? They are your principal stresses, where sigma 1 is greater than sigma 2, and sigma 2 greater than sigma 3. So what is very useful in design? It will be sigma 1, your first principal stress. That will be the maximum stress that's occurring on your structure. So if you're going to say, for example, you have solved everything and then you calculated in the structure, this is your sigma 1. So how do you know that your structure is safe? So you compare this one with a material property. We call that ultimate strength. So let's try to understand first why we are doing this one. So again, from this one here, so for example, we have sigma 1, 1, sigma 1, 2, sigma 1, 3, and then I have sigma 2, 2, sigma 3, 3, sigma 3, 3. This one is basically symmetric, but let's just consider that that is symmetric, and we'll try to prove that later on. We're going to derive all these equations later. So this one, like I said, we can rotate it in such a way that this one will be equivalent to a sigma 1, sigma 2, and sigma 3. So here, sigma 1 is the maximum tensile stress, while sigma 3 is the maximum compressive stress acting on your structure, and sigma 2 can be in between sigma 1 and sigma 3. So this one will be arranged in such a way that sigma 1 is greater than sigma 2, greater than sigma 3. So what is important here really is sigma 1. Why sigma 1? Because it's the maximum tensile strength that that's going to break your structure. And to which value do we compare this one? The ultimate strength of your material. So as you can see, that stress acting on your material, say this one here, must be less than the strength of this material, yes? Otherwise, it will fail. So, for this one to be safe, this one must be, less than that ultimate strength. So this one is a material property. So this one is taken from tests. So it can be metals or anything brittle. So you will be able to say that your design is safe. But this one is basically for brittle materials only. So this one is useful for brittle materials. Now, normally what designers do will add in a safety factor. So you have heard of that, yeah? So you have a safety factor, meaning that in order not to really go near that limit of failure, you add the safety factor. This safety factor, will take into account the different presence of defects in your materials, some material discontinuities, or even the environment that you have. So you have a safety factor there. So where do we incorporate the safety factor here? So if we have, say, an N, a safety factor, so how will you use that now in your design? So your safety factor, of course, can be, the environment, effects, or this can be the use. If it's too extensive, it can be located in a location where the weather, extreme weather, temperature can be from very, very cold to very, very hot, extreme weather conditions, and so on. So you have this safety factor. So how do we incorporate this one now? So assuming you did all your calculation, you have now your maximum stress. So this one must be greater or less than or equal to your ultimate divided by your safety factor. So you try to decrease that material property, the strength of the material, and then you equate that to your maximum principal stress. So now you have a failure criteria where your design will be based. So you have done all these beautiful drawings of your design. You cannot solve it analytically because the structure is complex. You go to finite element, and then you solve this one, you get your maximum principal stress, and then you relate that to your material property divided by your safety factor. There you go. So if somebody will ask you, how do you know that your structure will not fail? Then you have this one to show that your structure will not fail. A very simple equation, but the process for this one is not that simple. Yes? Now, moving on, there's also this so-called, I'm just trying to give out this equation at the moment. I really would like to derive this one as we go on, but I really would like to derive this one later, but at the moment it's just giving you an idea first, that we will also be looking into this so we have also ductile materials. Now, instead of the principal stress, you're going to use the von Mises. Now, some of you may also be able to encounter this one. What is the von Mises stress? So there's an equation to calculate that, the von Mises stress. And this one can be also determined using your stresses here, or simply this one's here. So you will be able to solve for the von Mises stress. And this one is pretty much for ductile material. But then again, if you're going to compare this one with a material property, you won't be using now your ultimate strength. You're going to use yield. So at the moment, of course, you can now incorporate your safety factor here if you want to. So again, that safety factor will be dependent on the use, environment, and so on. You can look at your textbooks or any other reference to determine the value of n. But for designers, you should incorporate the safety factor here. So you have a term called what? Design strength. So that design strength must be greater than the stress acting on your structure. Yes? So, very simple concept, but to be able to get the correct value of stress or strength, or sorry, the stress, to be able to get that, I mean, that's a very complex process. So of course you can now use some of these concepts to be able to solve your homeworks or practical assignments. So we're not just looking into 3D. If we can simplify this one into 2D, then we can also get the principal stresses for 2D structures. So take note, this one, you just rotate it in such a way that you get sigma 1 and sigma 2. So this one is equal to that. Principal stresses. So this is how you solve for the principal stresses. So I'm just showing the equation at the moment. No derivation at the moment. No derivation, is just simply presenting the equation. And then afterwards, we'll try to get the value of the principal stresses. So that's the definition. There exist three mutually perpendicular planes on which the shearing stresses vanish. So all normal stresses. These are the principal planes, and the corresponding stresses are the principal stresses. So as you can see, this is that equation. Okay. We'll explain it later. So this is that, and this will be your normals. So take note, just the definition. This is your normal, Kronecker delta. This one is your 3D stresses. This will be 0. So if this one is equal to 0, your normals cannot be 0. So what should be 0? This should be 0. If that is 0, then of course we can now determine the principal stresses. So simply take the determinant of this matrix, and then you can now solve for your principal stresses. Well, there's an equation for this one to be able to solve the principal stress, but let's just try to solve it. I mean, start from first principles and see how are we going to get those principal stresses. So this one, the determinant of this one, or this value must be 0. So the determinant of this one must be 0. So you just add their stresses, your principal stresses, and then simply take the determinant. determinant of this one must be 0. So let's take this one here, sigma 1. So that is now, so what's the determinant of this one? So what's the value here? This minus this, yes? Sigma 2, 2 minus sigma. This minus that. Yes, that's your first value. And then you take your second value, please correct me if I'm wrong here, minus sigma 1, 2. And then this, oh sorry, that's multiplied by sigma 3, 3 minus sigma. Okay. This minus that. And then you have now this one here. This. Yes. And then you have plus sigma 1, 3. Yes. So again, after doing that, all you have to do is just simplify this one. And then, of course, you will get a cubic equation, or the maximum, okay, or in the, this one here, the maximum value for this one will be in, what do you call this one, sigma cube. Or will be expressed in terms of sigma cube, that is. The power, the power, maximum power here is cube, sigma cube. So there you go, that's how you got it there. So that's how we go to